Did you want me to share or you want to share?
You okay to start and then I can take over?
Okay. Okay. Let's get started. Ignore all the. All right, everyone. Welcome to day 4, the penultimate day, the day before the final day of the end of Code Astro. We have one more set of lessons for you before tomorrow, where we just mostly share what everyone has built in the last week. All right, so our usual reminders, we have our anonymous feedback form. Please give us feedback anytime you want. We'll continue to remind you about it once a day. And our usual reminders to ask questions, ask them often. You can ask them in the chat box, ask them on Piazza, or ask them on Discord, and we'll try to monitor all of these various medium throughout the workshop and answer any questions in any of these ways. Just a reminder about group work. Spend the first 10 to 15% of the time. Oftentimes it's just a couple minutes thinking about what you want to do. Don't try to jump in right away. This is a good practice when coding. First, just like instead of just immediately start typing, right? Think about what you want to type, how you want to type it. I think the roles thing we don't really need right now. Okay. And then by the end of the workshop, just a reminder, you'll be able to use the language of software development, develop and release an open source astronomy package, and write code that follows the best practices of software development. And specifically for today, you'll work on actively avoid discriminatory behavior when coding and to write a test based on anticipated use cases of your code. And today is the kind of the last day to work on your project. So your project tasks will be to add tests to your repo and try to debug your code so your tests pass. Continue the things you've been working on yesterday, document your code, package and upload your code to PyPy, and do all this with the kind of goal that another group should be able to install and run your package tomorrow for some nominal case of run. So like whatever you say is you should be able to install and do X, try to make it so your code can be installed and do X. It could be as simple as just making a plot. It could be as simple as running a function and getting a number, but just like making sure that that particular functionality can work. So for example, in our example, galactic orbits of stars package, maybe our goal today is to write doc strings for a couple of core classes and functions and add a tutorial in our README for how to use those core classes or functions. Or write a unit test that evaluates the performance of those key functions. If a user sets a degree range keyword, does the Gaia query still work or does it crash immediately? We add also end-to-end tests and make sure the whole package is working. We'll put our code on PyPy and try pip installing it on each of our machines to work through any installation problems. So this is the day where we kind of put all the pieces together. So should be exciting. And then we have one optional lesson today. It's on code profiling. If you don't know what code profiling means, it is basically, in this particular case, it's about assessing like how much resources does your code take, like how much runtime and things like that. How long does your code take? And in that sense, how long does each function take? Like what is the function that takes the most time to run? Things like that. Tomorrow, in the morning, we'll have project presentations in the second half of the synchronous session. The project presentations will go as follows. In the first 60 minutes, you guys get to optionally present to the whole conference. So each group gets about a 4-minute demo. So that's you have to be quick and succinct. So you just want to show off like maybe just a couple features, be able to some. I think last in the last couple years, uh, small fraction groups use some groups use slides. The other groups just had a live demo where they opened up the terminal and then typed a few things and showed that their thing worked. The bravest of groups asked for user input from the audience and did a live demo with user input from the audience. So just to give you a sense, but you only have 4 minutes. 4 minutes can go faster than you think. So it's you only have time to showcase one or two couple features kind of thing. If you're interested in signing up to present to the whole conference, there's a Google Doc here. You can access it from the day four intro slides on the day four README. We'll probably also send out this link on Discord. So if you're interested, sign up there. It is first come, first serve on time slots. Um, and then for the remaining 30 minutes, we'll have you break out with another group, and each group will try to install each other group's packages, and you'll get to see a live response on their faces as they try to install your package and see what happens. Um, and then for everyone here, please also add your project to the Code Astro database. It's just like, here's a project I made, even if it's during for the workshop. If you end up going beyond and like making your own package for your research, and you think you benefit from Code Astro, please also add that to the database. We're just trying to collect as many packages as we can. This is useful for us for future funding proposals for the workshop to kind of show the impact of Code Astro. So now, you can put your projects now, and then also if you ever make projects in the future, put them in there as well. It will help us immensely, I would say. Tomorrow, and the very big. Oh wait, one more thing, and then it sounds like this might be a lot, but we all believe that you can do it. That's why we accepted you to this workshop. So don't sell yourself short, and work through as much as you can today. And whatever you can work through should be great for the live demo, and we're looking forward to it. So do as best as you can. And then tomorrow morning, in the very beginning, we'll have a panel on industry software development. So these are we'll be talking with people who, including two guests, one previous Code Astro attendee, including who have transitioned at least from academia to industry. Some people could have transitioned back, but at least have gone to the other side, seen what it's like, and have some experience to tell you about that. So bring questions. I have a list of like fallback questions that I will just keep going through. But bring your own questions, and what have you ever had a question for what would it be like on the other side? What does those day-to-day jobs look like? What kind of skills are transferable? What are the skills I should be working on to make it transferable? What were the best uses of your time in academia to make yourself a great potential hire in industry? If you have the kind of those questions, bring those questions, ask them tomorrow. That'll be in the morning from 9 to 10 a.m. Central Time. And then, as our usual, I don't think we made any changes again in the last day, but as usual, if you haven't updated Code Astro repository in a while, do a git stash, git pull orange and main, and git stash pop to get the most latest changes of Code Astro repository. And that is the end of the intro slides. So I believe we are starting off today with testing. So Sarah,
Yep.
want to take it away?
Yeah. Let me share my screen. All right. Um, Still having finger issues, so we're not going to be full screen. But yeah, so today we're going to talk about software testing. I just want to do a quick note before I start that I'm going to do Piazza polling in this class. So I encourage you to take a second to open up Piazza so you're ready to answer. All right, so the goals of this lesson are that by the end, you'll be able to explain the difference between end-to-end and unit tests, understand why continuous integration systems add collaborative development, and also to write tests based on anticipated use cases of your code. So to start off with a little bit of motivation, testing is really important to ensure that a code is accurate and also that it's flexible. So astronomers, to some extent, all test their code. We generally write a function, and then you might run it and check that the output is similar to what you expect. But I think the jump from like being somebody who writes a test to being a software developer is that I think excellent developers spend most of their time writing and thinking about tests that might be useful for evaluating their code. Writing tests is not just writing tests is actually interesting in and of itself. It's a cool problem. It requires creativity, and it also requires you to try to anticipate as many use cases of your code as possible. Another really important motivation of testing your code is that testing ensures that your code maintains the same behavior over time. So you can imagine that if you build up a test suite of several different tests that you can run over and over again every time somebody makes a change to your code, for example, you can ensure that like in the future when somebody somebody who wrote a script using your code like 5 years ago, that script will still work because you've written a unit test to specifically evaluate that use case. So one of our goals for today is to get you in the habit of writing really extensive and thorough tests. So the point of this lesson is really just for you to practice writing tests. So one of the big goals of this lesson is for you to understand the difference between unit tests and end-to-end tests. So let's start by defining what a unit test is. So you can think of unit tests like testing the smallest part of your code, and end-to-end tests like testing the overall performance of your code. So a unit is generally the smallest testable part of any software. So this could be like an individual function, for example. Unit tests generally have few inputs and outputs, and the ideal unit tests only test like one step of the code. So you're not testing, in most cases, like multi-step processes. Those might be more considered end-to-end tests. You're trying to just test the smallest little bit of the code. So a couple of things to think about testing. If you've ever been around software engineers, you've probably heard the term edge cases. In general, we want to test that the output of a function is correct for every sort of conceivable type of input. And so edge cases are sort of unusual inputs in some way. So for example, if your code operates on integers, you want to make sure you test the input 0 or -1. If your code operates on strings, try some unusual strings, maybe strings containing Greek characters, for example. People often ask, how do you test plotting code? Because generally we can't it's hard to tell a computer that the plot is correct. Generally we need a human in the loop to look at the plot and say that it's right. For our open source packages, we generally recommend just testing that your plotting code doesn't fail so that it runs all the way through and then it creates a plot at the end. And then it'll be the responsibility of the actual maintainer to make sure that every once in a while you're looking at the outputs and making sure they make sense. One other important caveat is that you don't need to test on inputs that aren't allowed by your documentation. So it's important to test possible use cases of your code, but you don't need to test things that your code is not designed to do. So for example, if your docstring says that this function only operates on integers, it's okay to not test how it performs on a float. It's called an undefined behavior. So let's take a look at a real unit test from the Orbitize test suite. This is a function that essentially just converts from Cartesian coordinates to polar coordinates. So from x, y to r and theta. So I'll show you what, I'm going to take you through line by line and tell you what it's doing. So the first thing it's doing is defining an array of x's, which we're calling right ascensions, and y's, declinations. And you can see that I'm testing conversion of x, y to r and theta in every of 4 quadrants because I'm doing trigonometry. So I want to make sure that the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant all convert to r and theta appropriately. So I then have my expected outputs. So here, lines 65 to 67 are the expected thetas. And then I'm also testing a different mode of this function here, which is the expected outputs if I mod the angle by 180. Then I'm actually testing the orbitize function. So here I'm running our RIDECT set PA function. So that's the thing that actually does the conversion. And I'm doing it with and without this mod 180 keyword. And then the last important part of these tests is this series of assert statements. So if you haven't seen an assert statement before in Python, this just if it evaluates to true, it continues on like nothing happened. And if it evaluates to false, it stops the code, so it raises an error. And this is the exact behavior that you want for a test. You want your test to stop Python from running if it fails, and just keep running like nothing happened if it passes. Another thing you might notice is this pytest.approx function. This is to help you get around numerical precision errors. So you can imagine that like you don't necessarily want like the inputs 1 and 1 times 10 to the minus 15 to be evaluated to be not exactly equal in Python. So basically your computer can only have precision up to the numerical precision. So this allows you to test that these two numbers are approximately equal. You can either specify the absolute error that you can tolerate, or you can just rely on the default of this to make sure that your two inputs are equivalent to within the machine precision. All right, so now that I've defined a unit test, remember it's the smallest, testing the smallest unit of your code. I want to ask you what's an edge case we should test for the RIDECT to set PA function. So I'm going to open up this poll on Piazza. Day 3? No, day 4. All right, so please take 3 minutes to answer this. Awesome, we've got some really good answers. So some that I wanted to point out are one suggestion was to test conversion of 0, 0. I think that's a really great point. One other one that I didn't see but I think is worth testing is like if I have nans, what happens? How does it convert? And is that the appropriate behavior that I want for my code? A couple people were talking about like sort of not strange, but like edge cases of angles. So this function is converting from like x and y to angles. So we might want to add a check that like it never gets an angle that's greater than 360 or less than 0 if that's the desired behavior, for example. So we could add another assert statement that the position angles, which is the theta here, is not greater than 360 or not less than 0. For the one where we're modding by 180, in that case, we might want to check that it's not less than 0 or greater than 180. Yeah, another interesting set of answers that I got are testing different like input formats for the RA and DEC. So some people suggested like testing string values or testing like hour, minute, second formats for right ascension and declination. It's a little tricky because I didn't like give you the doc string for this RA DEC to set PA function here. But this sort of falls under like, is this actually a defined input? So I know because we wrote this code that it's not an input that's defined, that the RA DEC to set PA function is defined to work on. But you didn't know that, and if you if this function were defined to work on those particular types of inputs, then that would be a really important edge case to test. And that's in general just good to test like all different types of inputs that are allowed for the function. But yeah, I think like maybe the sort of base case level ones to test, base edge cases to test here are like x and y of 0, 0, something like nan. Yeah, awesome. Thank you so much for your participation. All right, so we've talked about unit tests. The next class of tests that I want to talk about are end-to-end tests, which evaluate a code's ability to perform its intended functions. So I've been talking a lot recently about user stories, which is the idea of like how does imagine what your user might want to come to your code trying to do. So and then try to test that like that whole thing that they want to do from start to finish actually works in the code. So we're testing overall the performance and accuracy of the code's main functions. And this is not necessarily like testing each function individually. It's testing that like if a user wanted to like use your code to run 6 functions sequentially and get an overall output, that overall output makes sense. So in general, that the way that users interact with the code works. This particular type of testing is not always amenable to continuous integration. We're going to talk about continuous integration in a couple of slides. That's basically the practice of running tests every time someone makes a change to your code. So you can imagine that if your code like takes a long time to run, you might not want to run a suite of end-to-end tests every single time someone makes a change to your code. But it is still worth maintaining a set of end-to-end tests so you can periodically run and make sure that your code is still functioning the way you expect. So in Orbitize, we do have a set of end-to-end tests that we don't run all the time, every time someone makes a change to the code, but we do have a couple that are fast enough for us to run within our continuous integration system. So we'll run this test every time someone makes a change to the code. So let me give you an example of this. So the overall purpose of the Orbitize package is to produce Bayesian posteriors given a set of input data. So one like user story is somebody comes to the code with a set of astrometric data that they want to get posteriors out for. So you can imagine that in order to go from raw data to posterior distributions, there's a lot of intervening steps. We have to like set up a thing that will then run a backend algorithm that will actually compute these posteriors. So this is an end-to-end test that tests that entire process. So let me take you through what it's doing. So first, we're setting up this driver object in Orbitize, which is the thing that actually like performs all of these computations and stores information about the individual star system that we're working on. Then these next two lines, 18 and 20, will actually run the posterior calculation. So here we're actually like sampling 1,000 possible orbits from the posterior, and we're saving them in this orbits variable. The next thing we're doing is computing marginalized posterior, so individual orbital element predictions. So basically, rather than computing the, in this case, like the whole 7-dimensional probability distribution, we're just pulling out individual elements of that. And then we're comparing to the expected values. So we're running Orbitize, we're computing an answer, and then we're going to compare that answer to an independent implementation. So I'm just hard coding these values in. These are not like, these are just sort of ground truth values that we're comparing against. And then the last thing is we'll again use these assert statements and these pytest.approx functions to test that the values that we get are within 20% of our expectation. So again, this is testing like many different functions in Orbitize. There's like tens of steps between this step, which sets up the container for all of the information, and this step, which runs which actually runs the backend computation algorithm. So I now want to ask you, what's an example of an end-to-end test relevant for your research? And if you're not working on a research project right now, you could think about just an end-to-end test that would be relevant for any astronomy research project. All right, so let me open this up, and then I will give you again 3 minutes to think about it. All right, so take 3 more minutes. All right, awesome. I'm seeing a lot of really great answers. So some points that I want to make based on the answers that have been submitted so far. A couple of people submitted things that are pretty similar to what I gave you here. So an idea might be running an MCMC fit for a known system and comparing that the outputs are comparable to published values. A couple of people also mentioned simulated data. This is a really great example for end-to-end tests. Making sure that if you generate something where you know the answer, and then you run your code on that simulated data and it gives you a result, that it actually gets out what you expect. Another example is testing like independent hardware. So there was an example of like running a image reduction pipeline on data from one instrument and comparing it to the same image, comparing it to a known answer from a different instrument. One other point that I wanted to make is that a couple of people talked about like testing sort of weird values here. Generally, like end-to-end tests, you want to test end-to-end tests, think about testing like typical use cases of your code. So you're not necessarily in the end-to-end test regime trying to find like trying to test super weird inputs. Think about testing like typical ways that users might interact with your code. And in the unit tests, you're going to try to catch those weird edge cases. As you might know, as you might like infer, the boundary between these is a little bit fuzzy, and it's not actually super important to classify each individual test you write as a unit test or an end-to-end test. But I think it is important to like specify the difference between these two, because I think they're both important regimes to test in your code. All right, so I want to give you a little tour of the tests in Orbitize, what they look like, how they're actually set up. So we have, this is just the main Orbitize GitHub page. So you can see all the code lives in this Orbitize folder. We have a separate folder called tests.
Sarah, can you make the font a little bigger?
Yes, thanks. How's that? One more big.
I think it's good. Yeah.
Cool. So I was on the main page, and then I went down to this tests folder. So we have all of our unit tests live in the base level of this folder. So you can see we have all of these .py files that start with test underscore. And then we also have end-to-end tests here. So the end-to-end tests are not actually run every time we make a change to the code. These take hours to days to run. But we have, like, you can see here, we're testing that like if we run our code on a known system, Beta Pictoris, we get expected answers. We get the expected answers that's consistent with independent implementations of these methods. The unit tests, so if we go to, I think it's in test system, if we go down to, tech. Yeah, so here's where that unit test that I showed you before actually lives. It's within this test system.py file. So the setup of these is just, it's a bunch of function definitions. And then these will get automatically collected and run by our continuous integration system. One other thing to point out is that we've organized these more or less by the modules of the code. So remember, for a Python package, each individual .py file is its own module. So we've got like a test driver, test Gaia, test Hipparcos function, and all of these correspond to individual modules in the code. So we've got a Gaia, we've got a Hipparcos, etc. So we've written a like suite of unit tests that goes through and tests each individual function in that code, in addition to having these end-to-end tests that test the whole process of orbit fitting. All right, so for the next 30 minutes, I want to give you a chance to actually write some tests for some code you haven't seen before. So I've got a link here that, let me open it up to show you. So I wrote this class that you'll need to read the documentation for, figure out what it's doing. The first two things I want you to do are first think about your user stories. How would a user interact with this code? Write down a couple different ways that they might use the code. Also think about some edge cases that you might run into and think about as a developer. Then I want you to actually write some unit tests and end-to-end tests. So I've done a little bit of scaffolding for the first test, and then I want you to come up with your own unit test, and then also come up with your own end-to-end test. If you finish early, I'll note that the implementation of this is not perfect on purpose. And so I want you to think about how you might improve the original code and actually start implementing your improvements. And to think about how you could improve it, I would suggest thinking about like how users might break this code and how you could change the design to decrease the probability of breakage. So I'm going to give you 30 minutes to give it an honest try on your own, and then 15 minutes to discuss your solutions with your partner. At the very end, I'll walk through my own solution. So we'll take until 5 after, and then we'll do the sharing out with partners, and I'll call you back at that point. Okay. I'll also post the link in the chat. All right, best of luck. All right, I think at this point we can move into discussion. You can either discuss with one person or you can go back to your regular groups. I'll open the breakout rooms online. We'll take 15 minutes here, then we'll come back. I'll briefly talk about my answers, and then we'll take a break before finishing with the testing lesson. 5 more minutes. All right, welcome back, everyone. So I briefly want to go over what I wrote for this activity so you can compare it to what you thought. All right. So first, how would a user interact with this code? So one way I could imagine is just fitting a line or just fitting a quadratic function. And then the other way I could imagine is doing the full comparison and plotting the best fit. So using basically every piece of functionality of the code. Some edge cases I could think of were 0 data points, array of length 0, or 1 data point, all data points are 0, or data points perfectly define a vertical line with undefined slope. There's a lot more, maybe like nans in the data points. Data point, like if the user puts in arrays of different lengths, if I didn't explicitly specify that, you shouldn't do that. All right, so I want to show you first the first unit test that I filled in. So step 1, I created a time series to test on. So here's some data. I'm then going to instantiate the compare fitter class here. And then I'm going to run the fit line and then assert that the M and B are exactly or approximately what I expect based on the properties of the simulated data. Another unit test that I wrote, and I specifically did not write one for the plot parabola method because I wanted to show you how I would write a unit test to make sure that I'm catching errors appropriately. So in general, the way that the code works right now is that if you put in an empty array, it returns an error. And in fact, the error is a type error. So what you can do if that's the behavior that you expect and you want your code to throw this error every time a user puts in this incorrect type of data, you start off everything the same. You instantiate your fitter class with the type of data that you're trying to test. And then you can just try this try except statement. So if we accept the particular type of error that we expect, you can then just continue on with the code. And that's a perfectly valid unit test. It's good practice to only catch the type of error that you expect. So you might sometimes see rather than except type error, just like try except. And the function of this will be anytime any error happens, the code will pass. So that's not great, great design because you don't necessarily want to test that your code passes anytime any error happens. You just want to test that a particular type of error is caught as expected. So this error specification is a little bit better practice. And then I've got this end-to-end test that I wrote, which actually requires manual inspection of the final result. So it's sort of better suited for an end-to-end test. This would be harder to run automatically and have a computer determine if it's correct or not. So I'm, in this case, generating some noisy data and then running our code as a user would. So I'm instantiating the compare fitter class, then running fit line, then run fit quadratic, and then plot the best one. So you can see that I'm actually like plotting the best fit. All right. All right, so how would you improve the code? So a couple things that I could think of, I think there are many, is that first it would be good to add some more descriptive error messages for the empty array case or the one element array case or the vertical line or perfectly horizontal line case. Generally, you don't have to catch every single error that users might introduce to your code. It's totally okay to not catch errors that aren't allowed by your documentation. However, users appreciate it if you return descriptive error messages for common errors. So if you anticipate a common misunderstanding of your code, it's a nice thing to do to return a descriptive error message to help the user figure out what went wrong. So I was thinking that right now, NumPy polyfit is the thing that's actually catching the error for the empty array case, and that error might not be super helpful for users. They might not know what part of the code they have to fix. One really big issue and something that I actually did in this code on purpose to show you some of the perils of object-oriented programming is that right now the code breaks if you don't run fit line and fit quadratic before plot best. So if we look at the plot best, oh, that's the unit test. If we look at plot best, we're assuming that self.linear resids and self.quadratic resids are defined here, and they're not actually defined by default, they're defined by running these individual methods. So this is a really common like pitfall of object-oriented programming, that your code can fail depending on the current state of your individual object. So maybe that's the behavior you want. Maybe you don't want this code to run if you haven't run those two things first. But I think two potential ways to think about getting around this. A would be at least documenting it and telling users you cannot run this function if you haven't run these other functions first. Or, for example, like fit line and fit quadratic are both pretty quick functions. They don't take like, seconds to run. So I could just maybe put them in the initialization of this class. So they run automatically for the data, and then a user can, so here, let me actually show you where that would go. So rather than having a separate fit line and fit quadratic function that only define these self.quad resids and lin coefficients and lin resids, if the user chooses to run those methods, I could just put this functionality in the initialization, and then they'll always be defined. So that's one potential improvement. All right. And then the last improvement that I was thinking about is that if we're running this many times, for example, if we're like running this in a script and we're doing this for like hundreds or thousands of, individual data sets, we might not want to make the plot by default every time. So a nice thing if you have the functionality to make a plot is just to add a keyword of like make plot, and you can toggle that on and off. Another even better thing would be to separate out the plotting and numerical comparison functionality into separate methods. So a user can very easily choose to, and it would be very clear to a user that like, this is the function I do to actually do the numerical comparison and define this, the best fit parameters of the thing that I've chosen. And this is the code I use to actually plot those results. All right. Any questions before we take a 5-minute break?
So there was an interesting question, maybe it's on Piazza, but it's relevant to what you discussed. Somebody asked, is it okay to bunch separate unit tests into one giant single test function and test for a grid of different issues? Is it the best practice, or keep it separate?
Yeah, that's a really good question. I think in general, you want your unit test to not have too many different things that they're testing, because if it fails, you want to know what's failing. So if you have like 40 different things that you're testing, and then your code says, oh, well, like test everything failed, that's not necessarily going to help you as a developer figure out which test is failing. So I generally don't, I will, it's probably best practice to have an individual unit test for like each individual thing that you're testing. I tend to have like 2 or 3 different things that I'm testing per function. So I might have like, you saw in the RA deck to set PA that I was testing like with and without a particular keyword for this particular function. But yeah, generally like putting too much stuff into each individual function is not great practice. Yeah, really good question. Thanks. One question on Zoom was, does plotting usually take a long time? It depends. Plotting definitely takes longer than not plotting, and often plotting can take a really long time. So yeah.
Oh, we have a question here.
Mhm.
Good idea. A lot of information maybe from your previous functions that you can check that the whole functionality of your code works, or is that not a good end-to-end test?
So the question is testing if a plot if testing a plot a good end-to-end test, because sometimes a plot would incorporate a lot of different functionality from various other functions, or is that not a good way for an end-to-end test to
Yeah,
function?
totally. No, I think plots are really good ways of doing end-to-end tests. And that's also something that makes a lot more sense as an end-to-end test than a unit test because it's very hard to tell computers to evaluate whether a is correct or not. But that's something that you, as the expert developer, can do very easily. So yeah, I think that makes total sense.
Another question on
Right? You got the plotting objects. I don't know enough about how things go through versus where the objects are created. Would you do some sort of like backend similarity comparison to see if the plot that is put out now is the same as the plot that was generated? Supposed to be a test, like store the object or something.
so the question is since matplotlib does output an object and all the pieces of the plot are in the object, is there a way to go into the backend and just like check similarity of like what the each of the markers and things like that are versus what you'd expect, or is that not a good way to go about it?
Sure. I think you could, for example, like check that the line that's plotted has the correct like individual like arrays that that define the line. Um, I think like it it uh, it depends what you're looking for. So, for example, you might have a stochastic thing. So you might be running an MCMC, and you could like check that your like corner plot you could check that your corner plot median is approximately the same as what you expect, but I think that's also something that you don't necessarily need a plot to do. Um, I feel like I'm kind of talking in circles. Sometimes plots show you things that are hard to define numerically. If you can define it numerically, I think it's good to check it numerically. But yeah, sometimes the plot will be helpful too. Any other questions?
We have one more.
Okay.
So the question was for something like for this code, would you want to make the plotting function return something like whether uh, the model used was linear or quadratic just for testing purposes to have an extra return to like tell you if it was a linear or quadratic fit?
Yeah, I think that's a good idea. Another good practice is that we talked about in the matplotlib lesson is that it's also good practice if you have a plot that's making a figure to return the figure object to the user so that they can modify it if they want to. So yeah, probably the things that I'd recommend returning here are like any new information that you got from the method. So like which was actually chosen, and then also the figure object that resulted. All right, let's take a 5-minute break. So we'll come back together at 34 after the hour, and then we'll finish up testing and then go to the anti-discrimination lesson. All right, let's get back started. Share my screen again. All right, so we spent the first half of the lesson telling you about what to test and the difference between unit tests and end-to-end tests. The second half of the lesson is more about like how to test. So the Python program that pretty much everybody uses to automatically perform testing is called PyTest. And this is basically this thing where all functions beginning with test underscore are collected and then executed, and failures and warnings are reported to the user. You all already have experience with PyTest because in getting set up for the workshop, we had you run PyTest on the Orbitize test suite in order to test that everything was installed correctly on your machine. And that I hadn't introduced any errors into the Orbitize code base recently. So let me show you how this actually works. So this is Orbitize on my computer. We're going into the test directory, and you can see that everything is named, all of our unit tests are named test underscore something.py. So the PyTest framework only collects things within these test underscore.py functions that are functions that begin with, the cells begin with test underscore. So the way that you would actually run these automatically is you just type py.test. I am not going to run the whole test suite. I'm just going to run one functions test. So all you really need to do is py.test from the root directory. But in this case, I'm only going to run one test. So if we run this, you can see it's collecting. So it's finding all of those tests. That's the first thing it did. You can see it's got two little green dots. That means that it ran two tests successfully. So it's testing this one planet, and then it's also testing arbitrary absolute astrometry. And those are the only things that it actually runs through in there. You can actually also define helper functions here if you want other things, if you want to separate out some other code, and those helper functions, if they don't start with test underscore, will not be collected and run automatically. It gives you a summary of warnings, and then it will fail if you introduce an error. So here we got 2 pass and 2 warnings. Let's artificially introduce an error so you can see what that looks like. So if we just add in an assert false, and then we rerun that same test, it's collecting, and you can see that rather than a dot, we got a little fail here. And it also shows us what failed and what line of code failed. So that's useful. I wouldn't necessarily say that PyTest is a useful debugging tool. I would, you can definitely use your unit test suite to perform debugging, but I wouldn't necessarily recommend doing it within PyTest. PyTest is mostly for automatically triggering your test suite. And we'll see how useful that is in other contexts. All right. So I've mentioned continuous integration a couple times at this point. Continuous integration is, no, it's not really a tool. It's a practice, a set of tools for maintaining your code's behavior over time. Yeah, it's a development practice where a suite of tests is automatically run each time a code is changed. I would say most continuous integration services that work for Python repositories use PyTest. So they basically just build a service on top of that runs PyTest automatically and in some nice way reports the outputs to the user. Generally good practice is for your suite of continuous integration tests or your suite of unit tests to touch as much of your code as possible and also to take no more than a few minutes to run. This amount of code that your continuous integration tests touch is called coverage. So you might see on a lot of GitHub repositories, there's a coverage badge. So on Orbitize, we've got this little badge. So that basically means that when our test suite is triggered and run automatically, that 86% of the lines of code actually are executed in one of those tests. There's a little bit of a trade-off between trying to get your coverage to 100% and actually writing useful tests. Just because a code has 100% coverage does not mean it's bug-free. And just because a code does not have 100% coverage doesn't mean that they haven't thought about most ways that the code might be used. So generally try to make this number high, but it doesn't necessarily need to be your only metric. Think about actually your user stories. What are the useful ways that your code might actually be used by users? Useful ways that your code will be used by users. GitHub Actions is a free continuous integration services that's really useful for Python packages. There's a lot of different things you can do with GitHub Actions these days. It's a really useful service. I'm going to show you what GitHub Actions we've got set up for Orbitize. So if we go to the page, we go to Actions up here. So you can see in the left-hand tab here, there's a couple of different workflows. So each one of these things is something that gets triggered and run automatically in subset of situations. So these are called like events. So when some event happens, and an event might be somebody pushed new changes to GitHub, somebody made a pull request to main, somebody made a pull request in general, some subset of these things will be run. So the first thing is just our JOS paper automatically recompiles. The second is our suite of continuous integration tests. So that is the thing that actually will run PyTest and check that everything's working correctly. We've also got our documentation builder automatically set up to rebuild the documentation and test that the documentation is still being built correctly when somebody makes a pull request to main. And then also we have a suite of tests that run through all of the Jupyter Notebook tutorials. This one takes a little bit longer, so I've chosen to only have that triggered when somebody makes a pull request to main. So let's look at the continuous integration tests. So you can see which branch this thing was run on. You can see the most recent branch that I was working on was upgrading to pyproject.toml from setup.py. If you click on one of these, you can see that you can configure it to run for different versions of Python. So you can check that your code is compliant with different versions and that there's nothing that's introduced that's breaking your code in like Python 3.12, for example. So if we look at the outputs of one of these, what it's actually doing is setting up a whole virtual environment, installing your package within that virtual environment, and then running your test suite. So if we go down to here, this is test with PyTest. So if we open this up, you can see it's actually doing exactly the same thing that PyTest did on my own computer. It's just doing it in the cloud on this virtual machine. And then it's printing out a million errors. And then at the end, it gives us 97 tests are passed. The other thing that it will do at this step is actually calculate the coverage. So it'll keep track at each point. And you can configure this as well, of how much of each individual line of code was touched by the test suite. All right, so you can set up new actions honestly very easily nowadays. You just go to actions and you click new workflow, and honestly just sort of click through, and it'll help you figure out what you want to do. If you look at what was I going to say? I don't think I want to say anything about the config files. But yeah, I would encourage you to, there's also a lot of really cool actions that already exist. A lot of them are community developed too, so I would encourage you to check those out. All right. Another thing that's really been taking off, and I also mentioned it briefly when I was talking just now, is tools to control the environment of your tests. So these go beyond like having an individual conda environment that has particular versions of like Python packages installed, but actually control like the operating system or something that represents your operating system inside of which you can execute your tests. A lot of like pipelines nowadays are actually run also inside of Docker containers or virtual machines, so that they can like very precisely control like which versions of software are installed and what environment everything is run inside of. So the main advantage of this is that running inside of a Docker container means that no matter where you run the code, the environment is exactly the same. We went back and forth at the beginning of Code Astro for a while about whether we wanted to make a Docker container for all of you to use so that we wouldn't have to worry about everybody getting the environment set up on their own machine and worrying about Conda installation and stuff like that. And we decided that we didn't want to do that because we thought that managing Conda environments was a skill that we wanted to teach as part of Code Astro. But it's tempting every year because it's hard to get everybody's environment to work. All right, so just before we finish and go on to some more activities for you to get continuous integration system set up for your own package, I want to do a little bit of class source best practices for testing. So I would like to use Stack for this. If you haven't used Stack before, if you're on Zoom, just type Stack and I'll call on you. If you're in person, raise your hand and Jason will call on you. And let's try to come up with a couple of best practices. So this is not a trick question, this can be things that I've already said, but it can also be from your own experience. What are some best practices for testing? All right, so let me know if you have any thoughts.
I'm
Jason?
gonna try to use the microphone
Okay.
and see if I don't have to repeat the question. Let me know if you can hear it.
Okay, sounds good. Excellent. I'm imagining Jason just running around the room.
Nice, the microphone is working. Sweet. Yeah, so one best practice that I like to use is when checking for errors in a code to use something like pytest.raises or unit test assert raises to check that an error actually happened. Because if you do like try comma and like accept, if the exception isn't raised, your test will still pass. But if you use something like pytest.raises, like division by zero exception, if it does not raise the exception, the test will fail. So
Nice. Excellent. That's a really great point. So just to repeat what you're saying not to just like do this try except because it will still pass if the error that you expect wasn't actually raised. You can use something like pytest.raises to check it will fail if that exact error was not raised. Yeah, that's a great point. Thanks. Other best practices. Again, not a trick question, so feel free to restate things that I've said.
Think of lots of edge cases.
Yep. Test edge cases, lots of edge cases. I think that's what you said.
Yeah.
Cool.
Testing for small units.
Yep. Testing smallest units of code.
Hey, this is L online. I have one, which is I try to write tests as I'm developing the code, not waiting until the end. And so whenever I get to a stage where I'm like, okay, I do need to make sure that this is working, I develop the tests alongside the code, and they kind of come out naturally, and then I don't have to think about them at the end.
Totally. Another practice that people sometimes talk about is test-driven development, which is you write the test before you actually write the code. So you're thinking very precisely about what inputs and outputs you expect from your code, and exactly what the functionality of the code should be. I honestly don't do that very often. I tend to do more of what Ella is suggesting of writing tests alongside code. But I think test-driven development is very good if you have like a very specific idea of what your code needs to do. Jason, was there another stack in person?
Hello. I really liked what you said, Sarah, about documentation, and also letting your own code tell you what's wrong rather than someone else's. Like in our test example, we had polyfit was raising the error, where we could write it in a way where we actually know what's wrong with our code.
Yeah. So let's say, I guess that's more about code design than testing, but that's a good point that we want to write code so that we return descriptive errors. And then maybe test that those errors are raised. Yeah, maybe one more idea?
Another thing to do sometimes is if I'm running a similar test, like if I'm running a test on a function and I'm just changing the input values, something you can do, I think at least in PyTest, is you can like parameterize the test and then pass in different sets of values, so you don't have to duplicate code so much.
Yeah, that's a good idea. Parameterize tests to not duplicate code. Parameterize. That's a good coding practice in general too. We want to not duplicate code as much as we possibly can, because you can imagine if you introduce a bug in or make a change in one bit of code, but you actually have that same block of code written like 3 times, it can be really annoying to have to update all 3 of those, and it's hard to keep them consistent. So generally refactoring code so that you're pulling out like code that's being used across many different classes or functions is a good idea. All right, thanks all. So here's my list of best practices. First, it's very similar to yours. So test as many use cases of your code as possible. Write both unit tests and end-to-end tests. Write tests throughout the development process, exactly like Elle said. You could even think about test-driven development. Something I also learned from Jason was turning debugging scripts into tests. So as you're writing scripts, when you're writing your code and debugging those are actually the things that your code secretly is being used for. So don't throw away those debugging scripts after you fix your bug, make them into unit tests. This is also a really nice way to make sure your test suite grows as your users encounter bugs. So if your user raises an issue on your GitHub saying, oh, I ran into this bug, and you write something to reproduce the bug and then fix it, take that script and turn it into a unit test afterward so that you ensure that that behavior that you fix stays the same over time. Also, like I sort of rambled a little bit about before, coverage is important up to a point. It's more important to test your code in all the ways your users will apply it than to get 100% test coverage. And 100% test coverage does not mean bug-free, importantly. Also, every time somebody asks me how they can easily get up to speed with a new code, I suggest that they write tests for the code. This is the developers will love you if you just randomly make a pull request with new tests for their code. They're going to be eternally grateful. And B, writing tests for code is one of the easiest ways to get familiar with all the different functions of the code. All right, so I'm going to give you probably 20 minutes now, maybe 15. What do you think, Jason? How much time do you want for the next lesson?
I needed like 30 minutes max, so however much you can have however much time you want, basically.
Okay, let's take 20 minutes then. So we'll come back at like 15 after the hour. So yeah, so these activities are to write a few unit tests and at least one end-to-end test for your package. I've linked to the Orbitize and another open source package, Radvel, the test suites for inspiration. I also encourage you to write your test using the PyTest framework and actually run PyTest locally on your test suite. the output product should be pushing the code for your test to your group's GitHub repo. The optional activities are to get GitHub Actions continuous integration or AppVer, which is one of these like virtual environment things set up for your packages test suite. Another optional activity is to learn more about Docker and get it set up for your packages test suite. I've got some example instructions here and an example implementation here if you want to check it out. Yeah, these things you will probably not do in the next 20 minutes, but spend a little bit of time and you can continue with your groups later this afternoon. All right, so we'll come back together at 15 after the hour.
And a reminder to open breakout rooms.
Thank you. 5 more minutes. Welcome back, everyone. Yeah, so I think we'll just take a 5-minute break from here, and then the rest of the time, we'll be talking about anti-discrimination. So yeah, see you soon. We'll come back together at 21 after the hour.
Sounds good. 5-minute break.
There's a student friend, so I.
Sorry, Jason, we can't hear you.
Muted. Okay, sorry, we'll have to start from scratch. Thanks. Thank you. All right, we're gonna do anti-discriminatory practices. So this lesson is a kind of, we'll first start off with kind of big picture things, kind of general landscape of kind of software engineering in general, and then we'll kind of narrow down to like things that you can do when you're developing your own package that are kind of best practices to avoid any sort of discriminatory behavior. And I just want to caveat this with, Sarah and I, when we wrote this is a very, we're both based in the United States. A lot of the topics we talk about are a bit US centric. We try to make it somewhat general, apply elsewhere, but there might be aspects of this where, it's very US specific and may not apply to other countries or cultures. So yes, we want to start off with just acknowledging that software engineering can and does contribute to discrimination. There's been clear cases in history where that does happen, and clear cases where it's still happening. So it's always good to reflect on and assess, how are we developing code? What is the impact of the code? Who is this for? Who is it benefiting, or who is it harming in particular when you're thinking about software? And we'll use a couple terms, so we just want to define them. One is the main thing we're going to talk about is bias. And there's kind of two kinds of bias. One is kind of explicit or conscious bias. This is where discriminatory action is intentional, clear, or overt. This is something made with intent. And then there's implicit or unconscious bias. And this is where discriminatory action is unintentional. The person doing it or contributing to it is generally unaware of it, or this is an effect. It's something that so like some policy was put in place, and as a result of that policy, there was some discrimination that happened, but that policy itself was not explicit in its intention. So, if you look at kind of just like who is working in kind of software engineering in the general in industry, we're not talking about astronomy here, just like in industry, there's been, it's quite skewed. It's potentially even more skewed than some of the sciences. Discrimination, some of this comes to especially, how people hire in software engineering. Sometimes you hear this idea of what's called like a culture fit. We're hiring this person because they're a culture fit, or we didn't hire them because they're not a culture fit. This is an idea that they want to hire people who are most similar to themselves, basically. And this has there's been a lot of documented cases of how this idea, this kind of principle, has basically cause, whether it's implicit or explicit, both racial and gender discrimination in hiring. And as a result of that, not as a result of that, but one of the things you see is that if you look at the workforce breakdown of the big tech companies, Google up until 2024, not this year, had released their diversity kind of report that showcases basically, how are they doing in terms of the workforce diversity. And you can see, how the gender diversity in the United States. You can also see the racial diversity in the United States, and how it's kind of predominantly biased towards men, and mostly also biased towards both Asian and white men. Of particular absence, there is no similar report for 2025, and they explicitly said that they are removing diversity-related hiring goals in 2025. This is much more of I would say, an explicit form of bias that they're doing. But why this is important? There have been studies that shown that more diverse companies earn more money. So like by having more diverse, by creating a culture where you actually can build a diverse workforce, you not only are tapping into a larger talent pool, you also have a diversity of ideas. And this has, for the companies that embrace this, they've shown compared to their counterparts basically to perform better just financially. And just as a note, this slide deck is on the day 4 README, and all these little things are hyperlinks. So if you're interested in reading more about any of these specific things, we have linked some articles or resources that we thought were interesting if you want to learn more about these things. So software itself is also not unbiased. Oftentimes you might hear this idea, software is just like math, it's just code, right? How could code be biased? It's just a bunch of ones and zeros doing its thing. And it's true that numbers are just numbers, and when you give it a certain equation, it's going to output a certain number. But oftentimes these codes are created with some internal bias, even if it's implicit bias from the developers. Uh, uh, some actually these examples, this is like every year we have to update the examples. We started this in 2020, and the update you'll see in the next couple slides. We've had to update these examples every year because these tools have basically have changed drastically. But one is idea is like if a developer has some sort of bias, or the training data, especially talking about machine learning algorithms, has some bias built into it, you're going to get that same bias uh, coming out of your algorithm, even though your algorithm itself is just quote unquote ones and zeros. So this has happened, historically. You've seen this in there's been like facial recognition software, or generally other software written that were like, oh, we can use your face to unlock phones or something like that, and it only works best for people of certain skin colors, because the developers, maybe if you look at the previous slide, were of particular ethnicities, and they tested it on themselves and like, this works great, but then they applied this to other cultures, other ethnicities, where people's faces may look different. And suddenly these things no longer work. Another way is, in the US, there's these companies that work with that actually try to predict where crimes would happen, and this is used by many police agencies around the country to kind of decide where to deploy officers, basically, and be like, we need to deploy officers here because this is where crimes are likely to happen. But in the past, there has been, a history of kind of discriminatory policing, that police would go to, say, neighborhoods, say Black neighborhoods or brown neighborhoods, where they think there's crimes happening, and find crimes, and that gets logged, and then suddenly they're like, oh, there's a lot of crimes happening here, so we should send more police people here. And then this is just a feedback loop, basically, where the policing, discriminatory police data is used to kind of predict where crimes happen, and then sends more police there to basically reinforce that idea that there's a bunch of crimes happening there. There's also search algorithms themselves are biased, especially these search algorithms are trained on data sets that are biased. This is an example from ChatGPT 2 years ago. Like, it doesn't even look like ChatGPT now, I think. Someone asked basically, please fill in the analogy. X is to man. Wait, X is please fill in X. Man is to X as woman is to nurse. And you can see that they completed this as man is to male nurse as woman is to nurse. So you can see how if we ideally, if you talk to a person, it'd be like man is to nurse as woman is to nurse, because they're both nurses. But here you can see how because there's biased training data that could induce biases in these algorithms, even though you're like, this LLM is just numbers and ones and zeros, but because this is the context in which the software is developed. This image on the right, this is a recent one where they also investigated various kind of biases in large language models and generative AI. And this is a image created with the Microsoft Copilot AI image creator, entering the prompt, the main character of a fantasy book for 14-year-old girls close up, right? Like, there was no instruction on the gender or the race or the look or any of this stuff. And it produced this kind of image, because this is kind of the stereotype of what it thinks this book should look like based on the input training data that it has. So is there things to consider, even though like maybe here again, the developers of the large language models or the generative AI models weren't thinking about this, but this is still implicit bias because this is still things that happened, even though that this wasn't their original intent. And people have been working on kind of correcting these biases, but correcting these biases isn't is requires some subtlety. So back in 2022 in Code Astro, we showed this is like the beginning of generative AI. DALL-E Mini just came out basically, and people were like this is this quality of AI generated images back in 2022. And we were like, let's make astronomers at a conference. They're like, oh look, astronomers at a conference. This is what astronomers at a conference looks like. You see, predominantly white men. You see telescopes, very small telescopes overrepresented at these conferences. People, this is kind of like, this is very obvious. There's a lot of stereotypes going on, a lot of implicit bias, and developers immediately went like, oh, we know how to correct that. We can just put in a cost function that just says that you have to produce like a diverse group of people anytime you generate people. And this is what happened in like 2023 and 2024. There's like, we forced every image from Google Bard to generate, if you ask it to generate people, it would generate diverse groups of people. And then you're like, ask me to generate a picture of a US senator from the 1800s, like, we know like historically that was also a biased group, but because you forced it to be diverse, now you've created this opposite effect in the opposite direction. So just because like you have this problem, and like this is what happens when you ask developers to solve like social problems, right? This is we're not trained in these things, and so these things require subtlety, and they require working with people in other fields to kind of get this right. And it's not like a one-line cost function thing fixes everything, which is what they originally did, as you can see. And then also, software doesn't live in a vacuum. Just because you develop a tool and is really powerful and it can be used for lots of good things, like generative AI, we find it very useful. It helps us with programming, debugging, searching things on the internet, but it can also be used in many nefarious ways, in forms of explicit bias, not by the people that developed it, by users that find it that use it in ways that are actively harmful. Right now with things like ChatGPT, fake news is now spreading is much easier to write than before. Instead of having someone to actually even write the fake news, you just have someone prompt ChatGPT to write the fake news article. And that gets posted on very extremely efficient advertising platforms that we have now to basically spread that news very effectively. And also as well, there's been with these generative AI models, they've gone from images to now video, and now deepfake videos of prominent individual figures saying things that they never said before is very easy to produce and something that we have to now watch out for. And there's I think this one I think links to an article where they have this someone did some research basically trying to figure out what kinds of fake news was generated with generative AI. And the biggest thing was like doing impersonations of other people, mass content creation, falsifying information, faking online identities, appropriating likeness, and also intimate imagery are kind of the most common uses of generative AI that are done in ways that's kind of explicitly causing harm to others or explicitly discriminatory. And maybe a little bit closer to things that you're using on a day-to-day lives. GitHub Copilot and other similar generative AI tools that are helping you code are very useful. I've actually used them for the last month because I hurt my elbow, and like typing with my right hand is actually really hard. So I can only type with my left hand when I'm coding sometimes. And because of that, I've been using GitHub Copilot to kind of autocomplete because I want to save my keystrokes and things like that. So it's, we recognize it's really helpful for us, right? But GitHub Copilot is also trained on basically everyone's GitHub repositories. And I don't think we understand exactly what how that works with the current kind of licensing and releasing of code. Think code that we release generally in the open source community is free for everyone to use. So ChatGPT learns off of or GitHub Copilot learns off my code. I guess that's perfectly legal within the bounds of how I release the code. But for other people, the code was copyrighted, or they didn't want or explicit permission was not given. But GitHub Copilot is using all that code to be smart enough to help you in your coding. The issue is that even GitHub recognizes that about 1% of Copilot outputs have snippets with at least 150 characters straight that match its training data. So basically, it's copying code from the training data and giving it to you. You don't know, and you don't know, what is the provenance of that training data? Is that training data coming from someone that's allowing them Copilot to share that code? Is that training data coming from someone who had not given permission for Copilot to share that code? And who's benefiting from this? Like, all this free open source code is on the internet, and suddenly GitHub, which is owned by Microsoft, is the one that's charging for this service and benefiting from this. One of the issues is, and I think this is resolving the courts to favor GitHub over developers, is whether developers should receive credit or licensing for what GitHub Copilot produces. And it seems like the courts are siding with GitHub, and that they do not need to receive credit for these things. Yeah, so I talked a lot of bad things about AI, and it is but we have to recognize that these new tools that are happening in big data and artificial intelligence and machine learning do provide clear, tangible benefits. That's why many people are using them. That's why we're finding them helpful in our day-to-day lives and workflows. So we want to be able to balance utility and harm in some way, right? I think it's clear that regulation is needed. I think there needs to be rules enacted to kind of set the boundaries for what is allowed and what is permissible and what is not permissible, and how do we identify and prevent impermissible things from happening. One of the challenges is, government legislation is slow compared to the development of these softwares. But there's still things that we can do. We can be judicious on how we use these tools and what they produce. One way to do this is, being careful on how you prompt generative AI tools, being critical of the analysis. Avoiding, if the AI tool provides you citations for you to cite, making sure that those citations are indeed real and indeed relevant to the statements that it is producing. One of the things I forgot to mention for Copilot is that Copilot, even though it does produce these 150 character snippets that are potentially identical to its training data, there's actually an option in GitHub Copilot to turn that off. And what it does is basically anytime GitHub Copilot produces a suggestion for you, it will actually check against its training set to see if that suggestion matches its training set. If it does, it will discard it. So that's an option that's off by default, but you can turn it on. And this is especially useful if you're doing an open source development and you want to release your code. You want to make sure you're not accidentally copying someone else's code. You can turn that feature on to make sure that if you're using GitHub Copilot, it won't prompt you training data that matches exactly its training set. It won't prompt you code suggestions that matches exactly its training set. The other things we can do, we can teach about these issues to others. Neither Sarah and I are kind of experts in AI, artificial intelligence, or any of these things, right? We're kind of learning it as we go, but as we learning these things, we're spreading awareness about these issues to others. This is why we're bringing it up here in this workshop. And the last thing, is we can advocate for more oversight. Government oversight legislation is slow, but it does happen. Not in the US right now, but in the European Union, European Union basically enacted a bunch of, or is proposing a bunch of AI regulations. Things like how you can opt out from being part of training sets for big AI models. Companies requiring companies to disclose how they acquired the data for their AI training sets. So it's not just here's our model, have fun. It's like, here's our model. We acquired the training data from this model from in these X different ways. And those were all the ones that we went into this training data set. And also things like prohibiting the blanket use of facial recognition software in public to basically not just have cameras everywhere that just identify everyone's faces as they are walking around. So these are things that are being enacted in the EU, and most recently, just in the last month, Google and other AI companies, I think like also, I forget, is it Facebook? At least Google has accepted that they would follow these principles. So they it's like a negotiation, right? Because if restrictions are too prohibitive, a company just be like, will refuse to offer services in your country because it's too hard to work with you. But on the other hand, if you're too lax, then the companies are free to do whatever, and finding this middle ground. And it seems like, these things are happening, and we can, advocate for other governments to follow this kind of principle. Okay, so that's kind of big picture, what's happening in the state of the world. We can also talk a little bit about like how do we want to develop software ourselves to make our culture welcoming and limit discrimination that's happening when we're developing code here, for our research projects. So one of the ways is don't contribute to an like explicitly exclusionary culture. Some kind of tips on that, one of them is like don't hate on other languages. So like don't tell someone I can't believe you're using IDL still for that, something like that. People are using tools that are best used for their purposes, right? If they're comfortable for it and it gets the job done, I don't think there's anything you can complain about. So, don't make other people feel bad. They probably recognize that, they're still using a language that most people aren't using anymore, and they really should transition, but maybe they just don't have the time, or there's just a lot of code that they have to rewrite and they just don't want to do it. And just don't have the energy or the time, the resources to do such a thing, so accept other people for where they're at in their programming. Don't micromanage other. This is actually kind of related to, a lot of Sarah's kind of in the first day talking about kind of some of the rules about how to interact when coding. Don't micromanage other people's code. Like being like, oh, you should be using iterators for that instead of for loop or something like that. As long as it's working. If they're open to suggestions, you can ask them if they're open to suggestions. But otherwise, if things are going swell for them, let them be. Don't minimize what other people are doing. Don't use statements like, it's trivial to implement, it's trivial to write unit tests for this package kind of thing. Um, you know, and then when you're developing these code bases, be transparent to, in like how people contribute to code. So like often, we often suggest to put in, one of the things we suggest to put in is like putting in a way of like, how can you contribute to the code? If you're interested in helping, make an issue, or if you want to, contribute to the code, like fork our package and make a pull request, like having those explicit instructions for how someone can contribute to the code. Or if you want to contribute to the code, email me. Having that explicit instruction makes it more accessible for other people to get involved. Don't judge other people's coding environments. Just because now you are all pros at VS Code, don't go back to your own institution and be like, look, oh, I can't believe you're still using Vim. Check out VS Code is so much better. You can do a little bit of being like VS Code can save me a lot of time, but don't make other people feel bad that they're not using VS Code. And embrace the growth mindset. Not everyone knows everything. This includes us. We're always learning as well. So embrace what you don't know, and embrace learning those things. Yes, embrace the diversity of skill sets. Not everyone needs to know everything. Some people are good at specifics, are only interested in learning specific aspects of being a good software programmer. Some people want to know everything. Some people want to learn this other aspect. So there might be a diversity of skill sets of interests of what people are good at, and also what people want to know. And attribution, giving credit where credit is due, making sure that everyone that contributes to your code is recognized. This is something that's important, especially in the sciences, where often people from marginalized groups often don't get recognized for their contributions to often very important work in the field. Some other more specific things, you can try to replace discriminatory language in your code. In the past, you might have heard of GitHub branches, the main branch being like the master branch. And then there's also this idea of using like, if you have like like two hard drives and one hard drive is copying the other, or you have two databases and one database is copying the other. There's like this thing called a master and slave relationship. This is all like from has very bad negative connotations, you know. And there, in fact, oftentimes discriminatory language is not only kind of makes people uncomfortable, it's often also imprecise. You can often have much more accurate terminology. So if you have two databases and one is the main one and the other one is going to copy it, you know, that can be a primary and backup. That could be a leader and follower, you know, something that's like much more descriptive of exactly what the behavior is. So you can use better language than maybe what sometimes is used as the default in the field. Same thing with blacklist, whitelist. You know, that's usually blacklist is like things that aren't allowed. Whitelist are things that are automatically allowed without any checking. You know, this can also just be a block list and an allow list. You know, this block list and allow list again, much easier to understand, especially from people that may not, you know, have learned English as their first language. Been in the U.S., you might have not heard of the blacklist and whitelist, but you'll probably understand what is a block list and an allow list. Oh yeah, the Git branch master has been now renamed to main for the same reasons. And then in astronomy, there's a real astronomy package that's called source extractor with that abbreviation. And it has over 7,000 citations. And the maintainer of the package, I believe, uh, doesn't want to change the abbreviation for it, but that doesn't mean that you have to use the same name that they want to use. You know, a lot of people have been calling source extractor SE instead. And this has been, you know, you can, and the community has, you know, you can embrace using that rather than using something that makes other people feel uncomfortable. Yeah, and building onto that, and it's just like using descriptive and professional variable names is good, and this includes not using swear words. You know, code is kind of the face of your software. You know, people, if you're giving code to the community, people might have interfaced with your code before they've interfaced with you as a person. So that your code is making your first impression of you to kind of professional colleagues. Bad variable names can make other people uncomfortable, and it also makes it harder to understand. I've given some pretty safe, vague names, but like, you know, things like not using curse words and things like that is also good. It's like, I think also Sarah had that example of one of our past TAs, Simon, on one of his job interviews, his interviewee just went through his GitHub and looked at all his code contributions. So you just want to think about someone who might hire you in the future, just going through your GitHub and looking at what the code you write is, you know, do you want them to see this? And so it's just good to develop this kind of habit of, instead of using vague variable names, which sometimes is lazy, right? Because it takes less brain power to write something. Maybe it's a little bit unprofessional, maybe a swear word, which I didn't put any on here. But like it might be lazy, right? Just gets the job done. But if it takes a little bit ounce of brain power, just get in the habit of just using informative variable names. And nowadays, you know, our computers have lots of hard drive space and memory. Adding in a few extra characters for your variable name will not cost your code very much in performance. And if you really, really have no idea what you want to call it because you really, really don't care about this variable, the Python standard is that if you really don't care about a variable, you name it a single underscore. Single underscore is the standard for for an unused variable name. So if a function outputs 4 things and you only care about one of them, you can name that one thing and then do underscore, underscore, underscore for the other ones if you don't care about them. And then, you know, as we're building software collaborations and now you guys are all working in teams, some other things to think about, you know, when you use code from other people, cite them or offer authorship to them if you're writing a paper. This is very important, especially for the open source community. People are writing code for free and putting it online for you to use. And there's no, like, the only way for them to receive credit or payment for that is basically attribution, citation. So like if you use matplotlib, if you use numpy, if you use astropy, you know, there are citations in the literature for you to cite for them, and that helps them because they know like, oh, there's a certain number of people that have used my package. This is why it's important for me to maybe in the future they want to apply for grant funding to hire a software engineer to help them maintain the package in the future, maybe 10 years down the line. Having that citation track record of success helps them argue that this is important for someone to give them money to do such a thing. Pay attention to whose ideas get noticed and credited. This is true for software developments and also just working in teams in general. Some people may talk the loudest, but maybe that's not just because you talk the loudest doesn't mean that that's the best idea. Thinking about who in the space hasn't provided their opinions, or who may want to provide their opinions in a different way. So making sure that everyone's ideas get noticed and credited. And along the same lines, maintaining an open and respectful communication with others. One other thing is to value collaboration over being absolutely right. This is like we should really be using iterators instead of for loops, right? But if this person helped you, give you an extra 500 lines of code to write a new feature for you and save you all that time, criticizing them, John, just, can you rewrite this all to use iterators instead of for loops? Maybe it's not the right way path forward for building an inclusive environment where they want to contribute your code, especially if that iterator versus for loop makes a 0.01 millisecond difference to your runtime of your code and doesn't really affect anything. Iteration is important. We're all kind of learning as we go. People, in social settings make mistakes, and sometimes policy ideas that we have for how things work don't quite pan out. We should recognize when that doesn't work. We should recognize when it does work. Make sure we keep doing the things that do work, and think about how we could eventually change how things don't work. All right, this actually should have gone 2 slides earlier, but this is when we talked about giving credit where credit is due. If you look in terms of computation, the history of computation in physics, one of the discoveries, there was a lot of women that helped that were behind the discovery of chaos theory. The idea that over time, for certain kinds of models, things will diverge drastically over time. This idea of chaos theory was done with the help of many women who were helping making the computation at those time. And only recently did we even know that they existed and had helped make those contributions. So yes, I think this is a link if you want to read more about it, but this is an example of where we want to make sure, paying attention of, who are the originators of ideas, who had contributed, and making sure that they get recognition for their contributions. If you run into discriminatory behavior in software development, maybe in your groups, maybe in larger teams, maybe, like what can you do, as a single person? One thing you can do is kind of redirect, because oftentimes maybe some sort of discriminatory behavior is implicitly discriminatory. It wasn't an explicit discrimination. Because of that, you can try to redirect it into a constructive action, try to change that attitude. Like if someone were using variable names that can make people feel uncomfortable, you can ask them, could you make your variable names a bit more descriptive, more of what they actually do? If someone's like, oh, this is trivial, you guys should be doing this, it'll be so much easier, it's much better for your code. You could be like, if you're familiar with how to do this, could you provide a code snippet or some example to help us get started, something like that. Calling out discriminatory actions is important. Oftentimes this happens implicitly and people are unaware. And so when you call it out, and maybe it will help them learn about this and again, change their own behaviors to kind of avoid this in the future. One thing we did with Orbitize is writing a code of conduct for how to contribute to a software package. This explicitly states what is allowed and what's not allowed, and also explicitly states the consequences for violating the code of conduct, such as we just refuse to work from you in the future, we'll not take any more pull requests from you in the future, things like that. And in the end, discriminatory behavior in software can be treated like professional discriminatory behavior in any other aspect of professional work environment, right? So your institution has resources and guidelines for reporting discriminatory behavior. So there's explicit discriminatory behavior, especially if it's happening for a long time. There are ways, for you to report this to people's professional workplaces, to their HR departments and things like that. These are they fall under the same umbrella as everything else in kind of professional life. Yeah, so just to summarize some best practices for open source packages that you could be doing. One is to use descriptive and professional naming, writing contributor guidelines, keeping track of and recognizing contributions. One way we do this in Orbitize is have a change log. So every time we release code, we have a few bullet points for what the new features are. And alongside each bullet point, we say who contributed to that feature. So this kind of gives us a whole history of who has helped contribute to the code. For larger packages, you can draft rules for the developer community, such as we talked about the code of conduct for Orbitize, and making sure that you credit the authors of packages you use in your code and in your papers. You can offer them citations, or if it's more important, maybe your co-authorship. All right, and we do have a couple minutes. I forgot I added these 2 extra slides. So that's kind of like discriminatory behavior in terms of kind of social things that are happening. One other kind of way we can think about discriminatory behavior in computing is kind of environmental considerations. Here, there's been a few studies on kind of the environmental footprint of astronomers. On the left, this is kind of the environmental impact per astronomer in Australia. And on the right is a table of the environmental impact. I think this is per institute, unfortunately, not per astronomer in the Netherlands. And just for reference, because all the numbers here and the x-axis here is in kilotons of CO2 emitted per year. For reference, a typical U.S. household emits about 7 kilotons. I think this would be kilotons of CO2 per year. No, 7 tons. Sorry, no, I'm right. 7 tons of CO2 per year. We don't need kilo and ton. Okay, it's 7 tons of CO2 per year, and this axis here is the average emission per astronomer. So you can see 7 is about here, and you can see that in Australia, supercomputing is kind of the dominant form of CO2 emission by astronomers. Whereas if you look in the Netherlands, you'll see that per institute, this is 50. This is 53 tons per year. This is 17 tons. It's much smaller, and that's partially because of what energy sources are being used. In Australia, there's a lot more usage of coal, whereas in the Netherlands, there's a lot more renewable resources powering their computing facilities. So thinking about um, what kind of energy sources you're using, what are the kind of potential impacts of those energy sources, and then thinking about that in the context of who is benefiting from the computation time and who is impacted by the effects of climate change. And those 2 things are often those 2 categories of people, who is benefiting from the computation time and who is being impacted by climate change, are often 2 different groups that may have some sort of discrimination bias in them. Okay, that's everything. And I think we are just at the top of the hour. If there are a couple questions, I'm happy to take a couple questions, and then we can break. Okay. Any questions? Okay, if not, I think let's end it here. So in the afternoons, we'll go back to our normal synchronous session. There's one more optional activity, and then remind everyone to sign up for presentations if you want to present. I see the schedule is like at least half full already. Yeah, so let's break here. Thanks everyone for joining on Zoom, and we'll see you tomorrow for the industry panel and project presentation.